Thank you very much for the invitation and for organizing this and for coming here. So I'm going to tell you about some recent work that is essentially the PhD thesis of Ori, a very bright PhD student, together with Edriss, Titi, and Hezi Gildor. This work is, in some sense, is it's still in progress, and it's about trying to couple chaotic advection back to the dynamics. So I've been working on chaotic advection tens of years, and I think and how to couple it back to the dynamics was always an open problem to us. I think David remembers this from many years ago, trying to think about weak vorticity on the background as being advected, etc. And in this work, we try to approach it in a different way, using some traditional models from that come from oceanography. So I will talk about density-driven flows. Just I guess this is probably well known to the audience here. Then I will spend a bit more time on chaotic advection because I understand it's not so, people here maybe are not so familiar with this field, so I'll try to give a bit more of an introduction to what is it about. Just remind you of what are box models, and then we'll introduce the new model that we have started to work on and the results we have on it. Okay, so density-driven flow, this is the basic idea that if you have a box with a denser fluid in one part, say kept by cooling this part, so this, you can think about this as cold water, and this is hot water, then beyond a certain critical difference between these, you expect to have here some recirculation. That's a very old idea that is beautifully demonstrated in these little videos of Bristol, and is thought to be a very major mechanism for important oceanographic currents. Most relevant for us, the motivating example for what we have been doing is the AMOC, the Atlantic Meridional Overturning Circulation, in which one think about cooling in the north by the cold weather there and heating in the south and causing this recirculation pattern. And one can also do lab experiments on it, and one can also think about estuaries as examples to such flows. So in estuaries, the density differences because of the salinity, and here in the ocean, there are in fact two competing factors: the salinity and the temperature, and we will get to it in a minute. So in principle, to solve this real problem, to really understand the appearance of the AMOC or its stability, one has to solve the full big GCM models, which are very hard to solve, and taking nonlinear PDEs for the velocity, the temperature, and the salinity, and the time-dependent boundary conditions, and all kinds of sources. And people, of course, do these things. The problem with these big models is that, as we know, it's very difficult to understand the cause and the causality of things, and we try to find, as many people here do, small models that try to explain what is going on. So this is just writing what I just said in equations. So we're looking at the advection-diffusion equation for the temperature and the salinity, plus some sources, and some nonlinear equation for the velocity field, and the density, which depends on the salinity and the temperature. One simplifying approach to understand such problems is to look first at what is called kinematics. So in the kinematics, you're saying, okay, somebody gave me the velocity field, solved the full equations, used some toy models, and let us just understand what a given velocity field does to a given passive scalar. And passive scalars, dye, pollutants, are pretty much can be think about as passive scalars, but people also try to think, is this also true for other scalar fields that may afterwards influence the velocity, vorticity, for example. But for now, you ignore it and you just ask, okay, given a velocity field u, what can I say about the field t? And there are two important limits. One is to think that I'm going to ignore the fact that there is advection and just use the diffusion. Now, the diffusion here is, of course, not a molecular diffusion, but eddy diffusivity, right? So and there is a big literature. I think people here are expert about these things on how to correctly model the eddy diffusivity so that the outcome of this equation will imitate what happens in real life. The other limit is to say, let us forget about the diffusion altogether and think about the advection. So this is when you take no diffusion and look at the Lagrangian point of view. The Lagrangian point of view says that if there is no diffusion, my temperature field is just moving with the flow. And therefore, if I know the particle path of this ODE, I know how the field is going to move around. So these are just the old-time characteristics that we learned in studying hyperbolic equations. But now the characteristics are not nice and straight lines because the velocity field is can be time dependent, it can be 2 or 3 dimensional. So it all boils down to understanding what this dynamical system do. Right, yeah, I assume incompressible flow. Yeah, I look here at incompressible flow. Yeah, otherwise you have to take into account shocks and things like that. But conservative flow for yeah, I will look at. Exactly. Yeah, actually, we actually have. I will just mention one, but this will be right. This will be a surface flow. Actually, we have some work on it. We've done some work on this, but that's for now. I will talk on incompressible flow. I will get back to this. Okay, so right. So if the flow is very simple, then if the motion, if the characteristic or if the particle paths in this motion are simple, then in fact the behavior is of course simple. And one of the beautiful experiments that show that are these Taylor reversible flow experiments in which you just rotate slowly the glycerin in a tank and you can reverse it and you get back essentially the same thing you started with. So in this case, when there's no diffusion, you get exactly reversibility. And if the diffusion is very small, nothing surprising happens. It's the same picture you have in mind of just dropping a dye in a fluid, and everything is quite simple to interpret, at least qualitatively. In fact, quantitatively, again, it's not so simple if you have stagnation point, etc. But we leave that. But otherwise, if there's not such symmetries, then the equations here, the solution to this ODE can be chaotic. This was already realized by Arnold in the 60s, that when the particle paths of this velocity field are chaotic, something very strange is going to happen to the mixing. Okay? And since Arnold's paper in the 60s, there were many works that showed such beautiful pictures in which you see that even though the velocity field, so all these examples, I guess, except maybe the ocean in which you don't know, but these are lab examples in which the velocity field is very simple. It is essentially just time periodic, and still you see that the shapes you get are of the passive scalar are very turbulent-like, right, and very similar to what you get in the ocean, even though we know that the ocean is not so simple. It's not such simple velocity field. So, and this led to many works in this field of what is called chaotic advection. I will not try to explain everything I know about it, which is of course only a small part of what is known about it. I will just, I think, I think for people not in the field, I would say one important, I think, concept that is very, I think, important for many fluid flows, not just in this context, is this understanding that the unstable manifold, or what is in finite time observation called the Lagrangian coherent structures, and the rotational cores are the observable structures in flow visualization. So many people prior to this learning about chaotic advection, people many times identified complicated looking visualizations as an indication to complicated velocity field. And in fact, what we realized in the 80s and 90s, that what one sees is really these unstable manifolds. And the unstable manifolds of this ODE, the x d2 dt equal to u, can be very complicated, and many times that's what one sees. So let me just say what do I mean by unstable manifold? Think about having a hyperbolic fixed point, a saddle point in your flow, okay? A stagnation point of your velocity field, which is unstable, okay? And then think about what happens when you put on top of it a blob of dye, okay? This blob of dye has to compress in this direction because this direction is compressing it, and extend in this direction because it is the unstable direction, the hyperbolic expansion. But it is held to this because it is sitting just on top of the fixed point. So it is held in place and is going just to get flattened. It's going to get flattened and elongated, but it cannot move away. Okay, so it gets flatter and flatter and longer. And therefore, no matter what you have here, if you have an oil spill or a algae or any kind of passive scalar, it is pinned to this point and just going to get longer and longer. Now, here I showed this little piece of the manifold which is close to the fixed point, or here these beautiful dipoles that we saw yesterday. So you can think about this stagnation point as say one of the stagnation point of the dipole, okay? And this just says that it's going to elongate along the, okay, here I put maybe the wrong way, as the other, yeah. So this will elongate this way, and here if you put here one, it will elongate this way, okay? Which means that if you put now, I want to go back to here. If you put, for example, on these things a big blob of dye, it will get, it will trace this unstable manifold, and you will see these lobes that are going away, and we saw it also yesterday in this talk about the dipole. So this is the characteristic thing that happens whenever you have a dipole which is unsteady, which is forced, say, by having an elliptic core or something like that. So whenever you see these nice lobes like that, this is a hallmark of a unstable manifold that is folding. And what you're seeing is basically signature of periodically forced system. Okay, it is very simple. Maybe so, and this picture comes to show you. So this is like this is like a very simple time-dependent periodic flow. This is a turbulent. Okay, this is a turbulent vortex ring, and what you see here, it looks very similar but has more structure to it. And this means that there is some kind of one dominant frequency, okay? And the other higher order or the tails of the frequencies are just making it a bit noisy, but the dominant frequency is what governs this thing. Yeah. Yes? Uh-huh. Well, in this particular case, this is from my PhD. Okay, this is basically point vortices with a periodic strain field. So it's the velocity field is as simple as that, and that's why this is this is the explanation. Here, it's my interpretation. You know, you can of course give more. In some sense, this is the Occam razor. This is the simplest possible explanation you can give. And let me show you one more example. Oh, I'm going backwards. Let me show you one more example, which I really love. This was also inspired by our work on this unstable manifold. This is a picture from the album of fluid mechanics of leapfrogging vortices. Okay? And when people saw these things from 78, there were many interpretations of what one sees. In particular, here, it was thought that the cores of these two vortices are merging, right? And that they are certainly deforming. So this was the interpretation of the flow visualization of these leapfrogging vortex rings. And then Sharif did a simulation of two vortex rings with a fixed core, circular core, that are leapfrogging, and it was just plotting the unstable manifold for these leapfrogging rings. And it looks exactly the same. So suddenly you see that this unstable manifold can explain things which can have much more difficult explanations, right? I mean, so.
The answer to this weakness.
Hmm?
The same more than one.
Right. As we know, you know, you can always make models more and more complicated, and I think you will not argue that a simple periodic flow is a simpler or a simpler explanation than something much more complicated that can also explain it. Of course, there's no uniqueness. I think there's no uniqueness. Yeah. Okay. So this is the one thing I wanted to tell about chaotic advection. So I said two things. One is that this unstable manifold is what one sees many times. These cores, these coherent structures that are many times, again, in time-dependent, time-periodic flows are KM bounded surfaces with a lot of perturbation. You can still keep it. And what I should also say that in these pictures right here, there is no diffusion at all. But again, there is a big body of work that says that if the diffusion is sufficiently small, you still see these structures, and this is evident by the pictures one sees in the literature, and also by numerical simulations in which one can check for how long do you see the manifolds when you have diffusion. Of course, as t goes to infinity, everything should be disappear. So, and maybe here I will just touch up about some more things we learned about chaotic advection without getting into details. This is just to raise some interest, and you're all welcome to talk with me about these things if it is interesting to you. One thing is, okay, so we understand that you have these manifolds and one sees them. What can you learn from them? So one thing, I think there was a beautiful talk yesterday about saying how many different length scales one can get in one fluid problem. And what I suggest is that these structures tell you that there are additional length scales. Okay, the additional length scales have to do with if you identify that you have such a homoclinic structure or heteroclinic structure and you have such manifold, then there is a length scale and time scale associated with it, because there is the time, there is the characteristic velocity, say away, so near the fixed points the velocity is zero, okay? Away from this fixed point there is some characteristic velocity which tells you more or less how long it takes to go from not too close to the fixed point to not too close to from a neighborhood of this fixed point to a neighborhood of that fixed point. So that's one time scale. And the other time scale is, and this is the time scale if you want, you have a velocity field, you take the time average of it, and the time average of it gives you this time scale. And then there is the main frequency from the first from the time-dependent part of the velocity field, and that gives you another time scale, and also the amplitude of these things, the ratio of these amplitudes of these things. This gives you, in some sense, a priori explanation on how big these lobes are and how narrow they become. Okay, so that's one thing that we've shown. The other thing is, of course, the question of what happens when you put diffusion on such flows. And as I said before, in some sense, when you have these unstable manifolds and you add diffusion, the more diffusion you add, the less observable they are going to be. So if you look at pictures in which of the ocean, in which you see a very nice separating surface, which is again something one sees a lot of times, and this surface persists for a few days, it means that it gives you an upper bound on the diffusion, because if you take this velocity field and detect this manifold and add more and more eddy diffusivity, now uniform in space, you don't try to make it, you get, and you see that in your numerical simulation, this boundary disappears. That means that the eddy diffusivity is below this thing, and that was this work with Dan Carlson and Eric and Hezi. So, and I think one of the most important parts here is to say that you can do such things provided you really take the velocity field to be time dependent. You don't want to do it with steady velocity field. So, because the unstable manifold for steady velocity field does not have these undulations. It's very nice and smooth and cannot mimic what one sees in life, whereas the time-dependent thing does give you that. And another work that we've learned about, and this goes back to David, to your comment about the surface thing, is what happens when you have three-dimensional flows, which are volume preserving, but your particles kept on the surface. And then, of course, you can get these simpler behavior because you have some attractors, which can be very simple. And finally, again, just kind of an advertisement, there are some nice external diagnostics that we can use to identify these structures, which are in some sense much simpler than finite time Lyapunov exponents, and would be very happy if people used it. Okay, so this is all about chaotic advection, and now let's go back to our problem. Okay, so we have these scalar fields. We understand that their motion for a given velocity field can be very, very complicated. But what happens if these scalar fields also influence the flow? The temperature and salinity influence back the velocity field, and in these pictures, we ignore it altogether. So the idea that came from talking with Hezi, who's a big expert in these box models, is to use the concept that Stommel introduced in the 1960s. So what Stommel said is that, in fact, these density-driven flows can be thought of in the ocean, can be thought of a competition between the temperature and the salinity. And he wrote a zero-dimensional model, in a sense, saying that we just have two boxes, north and south, that are completely mixed. So the temperature and salinity in each box is fixed. And since the density gets lower when the temperature rises and gets higher when the salinity rises, you have a competition between these two fields. And he wrote a set of ODEs, actually non-smooth ODEs that mimic these dynamics, and got a very interesting result that this dynamical system has, in fact, bistability. So you can have for the same parameter values, you can have one solution in which the AMOC goes from south to north, as it is now, or you could have it vice versa. And this became a very important work that was afterwards extended and was actually the same kind of behavior was also observed in GCM simulations, in which the parameter that was used was this freshwater hosing, how much clear water you put into the system in one of the boxes. Okay, so this is the box models, but as we said, it is difficult to see how to relate these box models, which have no spatial structure, to the Lagrangian picture, in which we have spatially dependent fields. And our idea was the following: let us go back to our temperature salinity equations and look at the velocity field, okay, that instead of it being coupled to the full dynamics via the Navier-Stokes, it will have two components. One of them will be, as in the advection, in the chaotic advection story, it will be predetermined and independent of the temperature and salinity. And the second part of it will be internally forced, so the form of it will be fixed, but its amplitude will depend on the temperature and the salinity, exactly as in the box model. So it will be proportional to the difference of the average of the density in one box minus the other box. So again, this is in pictures what I just said. We have one component of the velocity which is independent of the temperature and salinity, and, for example, could produce chaotic advection. You can think about the standard model of the Atlantic Ocean of the two gyres, right? And if it is steady, it is, if it is steady, it will have no chaotic advection, and if you move the boundary up and down, you get the chaotic advection. Again, these kind of models were heavily studied in this context of chaotic advection in the ocean. And then added to it another part which has again this one gyre, but now in the YZ direction. Okay, and this one gyre amplitude is coupled to the dynamics via the difference of the average of the density on one box minus the average of the density. If we have heavier fluid here, we will get this kind of motion, and if it is lighter, we will get this kind of motion. And the full three-dimensional toy model is this one, which is very similar to what we looked at when we looked at, but the toy model is in fact irrelevant to the general, to this general mathematical problem, which is this advection-diffusion equation with a eddy diffusivity, which is non-homogeneous, right? It is bigger in the horizontal plane than the vertical plane, with a mixed boundary conditions for the temperature and the salinity. And it is coupled to the velocity via the averages. So it is integral differential equation, right? Nonlinear integral differential equations, which are coupled together. In principle, as I said, it is okay, so there is one, this is the formal mathematical model, and for it you can use whichever velocities you want here and there. The question is what will be most relevant and most interesting for the ocean. So the way we took it was, for the toy model, we took the external field to be stratified, so it has no, its Z structure is just decaying in amplitude, but it's essentially the same double gyre that with exponential decay down to the mixing layer below it, it is essentially zero. It's in the mixing layer, you have the double gyre. In our toy model, in the simulations I will show, we have this double gyre that decays in depth, and it gets essentially to zero at some kind of a mixing layer, 500 meters, equivalent of, right? I mean, everything is non-dimensional, but that's the basic idea. So that's what we use, and in principle, you could use, if you want something from observation, right? It's not limited to this case. Okay. Yeah, for the toy model, right, and the analysis of this model, this where Ori and Edriss were working very beautifully on these parts, is showing the well-posedness of the model, global existence and uniqueness of weak solutions. I think most important physically, bounds on AI. AI is the coefficient in front of the AMOC, right, in front of the YZ flow. And in principle, you would think that in such nonlinear equations, it could blow up, it could, and it's not. It's actually bounded. There are a priori bounds on this. There are a priori bounds on the temperature and salinity gradients, and there is proof that there exists. So if you don't put any forcing to the, so if everything is steady, if the velocity field, the external velocity field is steady, then there is a steady state solution always for all parameter values. Again, this is, I think, this is not trivial solutions, right? Because the system does not have the trivial solution. You have boundary conditions. So there exists a solution always, okay? And for sufficiently large diffusion, it is also stable.
Global here is not
Global in time, yeah, not our
not
globe.
our.
No, our globe, but global in time, till the age of the universe, right? Okay. Can we relate it back to the box model? Yes. In fact, if you take the boxes and define the averages in each boxes and see what are the ODEs you get for the boxes, you get essentially the Stommel model, or the standard box model, form box models, with some perturbation that behave nicely, provided you assume provided you assume that the derivatives are not too sharp. Okay. Practically, can we get the bistability that people get in the Stommel model? Yes, we can. Okay, by doing the following trick: forget about the external velocity field and put the diffusion term to be strong in each of the boxes and very weak on the boundaries. So take a diffusion term which is spatially dependent. Okay, so in this way you practically get 4 boxes, and then you can tweak the parameters and see that you can get this bistability that Stommel saw. And moreover, if you increase more and more the diffusivity between the boundaries, you get to have a single stable solution as expected from the theory. So this is just a sanity check. What is more interesting is that if you now go back to our toy model and don't do this trick of changing the diffusion between the boxes, but take a uniform diffusion, you can also get and this is how the trajectory looks like, but let me skip that. Then you can also get the bistability. So this, in a sense, strengthen the connection between Stommel model and currents in the ocean. You can create these boxes by the fluid dynamics. So this one has external velocity. The external velocity here is the double gyre model without oscillation, and the double gyre is creating these practical boxes, because the double gyre makes, I mean, again, it is not a trivial result, in the sense that we have both the double gyres and the 3-dimensional flow. So the boxes are not really separated, but still we see that we get this. I mean, so this is the, say, the this, I guess, is the density field, okay? And you see that the density field is not divided to 4 boxes, but we have, but it creates the same bistability as one sees in the Stommel model, okay, with our model, okay? And this is trying to imitate the North Atlantic Ocean, and what is nicely seen here are these fronts. So again, what we put here, we have our toy model, okay? The boundary condition is just gradient of the salinity and gradients of the linear gradients of the salinity and linear gradients of the temperature. And here are this is the surface temperature, okay? And what you see is that you create these fronts, as we saw again in this chaotic advection thing. And if you take, say, 50 days oscillation, you start to see these wiggles that are also seen in the ocean and are also seen in these homoclinic tangles. So one thing we have not done yet, but I think will be nice, is to apply here these homoclinic scales and predict what would be the main oscillations that can create these oscillations that one sees here. And again, of course, we know in reality that there are eddies here and many complicated things, but this shows you that perhaps the dominant structure that make these things oscillate is just time periodicity of some kind. And again? The gyre, and so now you talk about the gyre, the surface gyre?
In the northern,
It's a double gyre, right?
if you lower the velocity, you still maintain that point.
Well, I mean, the point depends on the point. The 40 degrees is more or less where the gyres indeed meet, and I think as long as it is, I mean, we did not try it.
Only the branch, southern gyre.
We did not try it, obviously, so I don't know to tell you exactly, but my intuition is that if this will be weaker, maybe the slope here will be larger, but I'm not sure. I mean, one needs to about it. Okay, and this is to show that when we, again, this is our toy model, and these are our soda averaged fields. And we see that our very simple-minded toy model is not too far from that. We still have, and this is the AI that we get. So the AI is like a measure of the strength of the AMOC. So we get it to oscillate. The range is actually tuned to be on the right order of magnitude for the observed ones. So this is not. This is tuning of our parameter at this point. We still have some problems here with the density and especially density inversion, but these are things we are still working. So right now, in this toy model, the salinity and the salinity and the temperature boundary conditions are just linear gradients, okay? And there are no other sources. The purpose of this, No, we don't, right? I mean, this is the boundary condition is at the surface. The boundary condition at the surface is linear, but we have these fronts that are created, right? It is not, the flow itself is changing so it does not restore. Yeah, there are the boundary conditions are these linear profiles, and we don't get, right, it does not align with that because of the flow. Okay.
Do you see what this?
Uh-huh.
Right.
You are saying that we are not influencing the atmosphere. Is that what you're saying now? No.
We are within the ocean.
Okay.
But if you have
Uh-huh.
okay.
Yeah. I mean,
So it's dynamically, it's not a toy model to represent a toy model, but it is
of course, yeah. I mean,
consistent.
Yeah, because our velocity field is the sum of prescribed velocity. Yeah. Of course, yeah, locally, right. So to take into account the local dynamics of the influence of the temperature field and the salinity on the velocity field, you have to use Navier-Stokes, right? I mean, we are doing a toy model here. It's not Navier-Stokes, right? Right, yeah. I think for us, this is, if I'm not mistaken, is the, wait. Yeah. When I have to think about how it relates to it. Yeah, just a second. Okay, so yeah, I'll finish here and I'll get back to you on this. Yeah. Okay, so we are, as I said, this work is ongoing. We have the mathematical framework, which is explained in this paper. We still have some problems with density inversions, which we don't take care of yet, and we will. We are still thinking about the toy model for UE, if it is reasonable. Ori has been doing beautiful works now on trajectories, integration from real data, and we have some thoughts about how to change it a little bit. And what is upcoming, hopefully, in terms of sources, is how the Mediterranean outflow will influence this whole thing. That this was the motivating question to her PhD, and we hope to get to it at some point close by. And to summarize what I've been telling you, I talked a bit about chaotic advection, and the main message here is study the manifolds. And I introduced this kinematic-dynamic model that I think are giving another type of toy model to think about, and there's much work to be done here.